Hi, my name is Patrick Dallaire, and today I'm going to present the paper, The Indian Chef's Process. So in the Indian Chef's Process, actually the motivation is to learn the structure of a graphical model. And we want the prior that is the most flexible as possible. So basically, there's a couple Bayesian nonparametric priors that tries to infer the structure of graphical models. Probably the most well-known is the Indian buffet process, which is a prior over a single layer, but this hidden layer is infinitely wide. You have the cascading Indian buffet process that reuse the IBP and stacks multiple layers one on top of the other. And this prior allows for the inference of infinitely wide and infinitely deep networks. However, we are still quite far from pure DAGs. So the extended cascading Indian buffer process introduces skip connections, bringing us a little closer to what just pure DAGs are, but still we have the constraint that all observables are at the very bottom of the network and no connections are allowed between observables. So that's where the Indian Chef's process comes in. It's a prior over DAGs, infinite dimensional DAGs, accepts all connections between observable nodes. It's layerless, so connections can be from nodes that are hidden to observables or from observables to hidden. So the Indian Chef's process builds upon the beta process. The beta process is a probability distribution over random measures. It's a collection of beta random variables. And we can think of this as beta random variables positioned at different position theta k, which are also random from a Bayesian distribution H. And when you sample your beta distribution, you will have a probability pi k. And this can be thought as being the probability of some event occurring. And this event is the event theta k. And we will reuse basically this construction, the pi k and the theta k, to construct a probability over DAGs. In our construction here, we construct a probability distribution over the adjacency matrix. And in my example here, it's a 10 by 10 adjacency matrix because it involves 10 chefs. So the chefs are positioned according to a uniform distribution between 0 and 1. The connections are only allowed from top chefs to lower chefs, so from 1.0 to 0.0. And this is a constraint that forces actually acyclicity. All chefs will be associated to a popularity pi k, and this pi k is the probability for each node below them to connect to the chef itself. So the height of my chef here in blue is the probability that it will connect independently to all chefs below him. And Z is actually the occurrence of the connection or not. And we will sample the Bernoulli random variable to determine whether there's a connection or not. So here is an example of a random adjacency matrix. And we have different connections, but not all of them are interesting. So we are only interested in star chefs corresponding to observable nodes, observable variables. And we will only keep the ancestors and the observable nodes itself. So we can extract the sub-adjacency matrix and the subgraph involving the observable interesting nodes. So this means we can marginalize out easily all unconnected nodes of our network. And it's particularly useful when we let the number of nodes go to infinity, because we can marginalize them easily and keep only the sub-active graph. So doing the infinite limit and the marginalization, we end up with this probability distribution over sub-adjacency matrix, subgraph, and orders. and we use this to construct our MCMC operators. We demonstrate the use of the ICP prior over structures over DAGs to learn a layerless neural network where all nodes are actually stochastic. The pre-activation just before the nonlinearity are corrected by random noise, Gaussian noise. So if there's a neuron without any parents, it will still generate something. And we use this to perform density estimation. And we provide a training set. And the role of the inference is to reproduce a fake data set and to match the training set. We also demonstrate an application where we have to define whether two variables are independent. Here it's two independent random variables, x and y. So it's the y-axis and the x-axis. It's a quadri-model distribution. And we trained the model and inferred different structures. So we tested all structures from the posterior distribution for d-separation, and according to the set of posterior samples, we determine the posterior d-separation. And as the training set size grows, we get closer to a posterior independence test, basically. So this is a demonstration of doing independence test and d-separation with this approach. We also trained on a CNN. So we marginalize out the structure of our CNN in a special case of MNIST, where we only train on the 1, 2, 3 labels, because doing inference on the structures, it's quite computationally extensive. So we do random walk on CNN structures, and we do point estimate with atom optimization for the parameters, and we perform a random walk over all the structures of our CNN. And we were able to get a posterior ensemble that was accurate up to 0.95. So basically, the Donders process is a prior over infinite DAGs, a Bayesian nonparametric prior. It allows to consider the structural epistemic uncertainty, and I hope we will see more applications in Bayesian nonparametric deep learning later.